All right, welcome back, everybody. Chapter 3, Lesson Echo, Graphs of Other Trigonometric Functions. Objectives are to graph tangent, cotangent, secant, and cosecant. Transformations performed on them, and writing a function from a graph. So let's get it going. All right, so unlike sine and cosine, which are continuous functions with no vertical asymptotes or holes, tangent and cotangent have an infinite number of vertical asymptotes. So I want to look at the unit circle real quick to identify locations for these asymptotes. But recall first that the tangent of a function, or the tangent of theta, is always the y value over the x value in the unit circle. So our tangent at 0 degrees is 0 over 1, which is 0. Our tangent at pi over 2 is 1 over 0, which is undefined. Tangent at pi is 0 over negative 1, which is 0. Tangent at 3 pi over 2 is negative 1 over 0, which is undefined. You'll see this repetitive pattern where any factor of pi, right, 0 pi, pi, 2 pi, 3 pi, 4 pi, 5 pi, 6 pi, etc., we will get a value output of 0. Any factor of pi over 2 plus pi units, so pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, 9, 11, 13, etc., we will get an output of, actually an undefined output, so a vertical asymptote. So let me sketch a couple of vertical asymptotes here. At x equals pi over 2, excuse me, and x equals negative pi over 2, and I'll go one further on each side. This would be x equals negative 3 pi over 2, and of course over here x equals positive 3 pi over 2. Now we said at each of the pi locations, so 0 and pi and negative pi, and then again out here at 2 pi and on forever, we would get outputs of 0. Okay, now let's look at pi over 4. So at 45 degrees, I would have a y value and an x value that are equal. If that's true, then root 2 over 2 divided by root 2 over 2 will be 1. So we get an output of 1 at pi over 4. I will get an output of negative 1 at negative pi over 4. And the same will be true, or very similar, for negative 3 pi over 4, negative 5 pi over 4. And what you're going to see, guys, is that the tangent function takes on this shape, where as we approach an asymptote, any asymptote from the right, our function's limit notation would send the output to infinity. And as we head toward an asymptote, from the right, we would, actually I think I said that wrong in the earlier part, but as we approach an asymptote from the left, we're going to go to infinity. As we approach any asymptote from the right, we'll go to negative infinity. Now typically we kind of zero in on this first cycle of tangent. Okay, notice that the period, we'll visit this again later, is no longer equal to 2 pi, it's equal to pi units, right? The distance from start to finish on a cycle is pi units. Okay, cool. Let's take a quick look at cotangent. Now, cotangent and tangent are closely related, right? Wherever tangent equaled 0, cotangent will be undefined. And wherever tangent was undefined, cotangent will be 0. All right, so you can imagine that now instead of y over x, it's x over y. So at negative pi over 2, we're going to have a 0. But at x equals 0, we've got a vertical asymptote. Okay, so we're swapping our inputs for vertical asymptotes and zeros. So this would be negative pi. We would have output of 0 at pi over 2 and a vertical asymptote. I won't go through quite as much detail in the cotangent graph, but that would be true. Okay, so let's take a look at pi over 4 and negative pi over 4 real quick so we can form this graph. Okay, so the cotangent of pi over 4 would be positive 1, just like tangent of pi over 4 was 1. And the cotangent of 3 pi over 4, right here, this is pi over 4, this is 3 pi over 4, is going to be negative 1. So our graph will look like this. Very similar to tangent. Almost looks like a vertical reflection. However, it is not. Please don't mistake that. But that would be the graph of cotangent of x. Okay, let's get into a little bit more with all of this. So the various transformations used on sine and cosine also apply to tangent and cotangent except for b. So a is a vertical stretch, shrink, or reflection based on the value of a. B is a horizontal stretch, shrink, and reflection as well. However, B, it's no longer 2 pi divided by b gives us the period. It's now pi divided by b gives us the period. So that's the one change that we're going to see with tangent and cotangent. Okay, phase shift, no change. So our values for C. And vertical shift, absolutely no change. So let's get into a couple of examples. Okay, so I'm going to graph the parent function cotangent of x, and then we'll make some adjustments on it. So let's sketch cotangent of x. I'm going to do just one period here from 0 to pi. Recall that cotangent had a vertical asymptote here at x equals 0, and another at x equals pi. It was 0 at x equals pi over 2. It was 1 at x equals pi over 4. And it was negative 1 at x equals 3 pi over 4. So here's what the graph of cotangent of x is equal to. Now, what I'm going to do is I'm going to do my horizontal transformation first. Then I'm going to do my vertical transformation, specifically the stretch, and then I'm going to shift the function down 4 units. So let's work with this value for b. 3 is equal to b. Therefore, the period is equal to pi over 3. Remember, this is now pi divided by b, not 2 pi divided by b. Okay, so what that's going to do to our graph, and I'm just going to do a quick adjustment with some numbers, is that's going to take and divide all of our current inputs by 3. So now this x value will be pi over 3. This x value will be 3 pi over 12, which is pi over 4. This x value was pi over 2. Now it's going to be pi over 6. and this x value will be pi over 12 if I divided that by 3. So I've just, in this case, readjusted my values for the inputs. Okay, no change in the scale of the graph at all yet. All right, now the next thing I'm going to do, our amplitude is 2, our a value. I'm going to change this to 2 and this to -2. I have not changed any values on the graph or any scale on the graph, or I've changed the scale. I haven't changed the actual look of the graph. All right, now what I'm going to do is finally our d value is -4, so I'm going to shift our function down 4 units. Okay, this is where it gets a little dicey, but I'm going to shift this point down to there. I'm going to shift this point down to here, and I'm going to shift this point all the way down to -6. All right, so we no longer have a midline like we did for sine and cosine. The vertical asymptote location has not changed, but this is the point pi over 6 comma -4. This is the point pi over 12 -2, and this point is pi over 4 comma -6. All right, so we've taken that function, we have horizontally shrunk it, vertically stretched it, and shifted it down 4 units. All right, let's look at a tangent function. Okay, very similarly, I'm going to put the asymptotes up, and tangent had asymptote at -pi over 2, as well as pi over 2. Had a 0 here at 0. Wow, this is not like well sketched, but that's okay. Alright, so pi over 4, 1, and -pi over 4, 1. I hope you can deal with some of my inaccuracies here. Okay, so what are we doing to this thing? Let's do the horizontal transformation first. My period is going to be pi over 1/2. So it's going to be 2 pi. Let's see, we're going to have a vertical reflection and a shift up 1 unit. Okay, so what I'm going to do is then I am going to multiply my current period by 2. Okay, I'm going to double it. Right now this distance is pi units. I want it to be 2 pi units. So if I multiply these by 2, I'd go from -pi to pi, which would make these values, instead of pi over 4, they would now become pi over 2 and -pi over 2. Okay, I'm going to do a vertical reflection. Okay, vertical reflection would put this point here, right here, this point here, right here, reflecting it across the y-axis, or the x-axis, excuse me. And now I currently have y equals -tan x over 2. Now all I got to do is add 1. Let's add 1 to the function, moving this point right here up to 2. Moving this point right here up to 0.01. Moving this point right here up to that location there. Again, vertical asymptote locations do not change. And I get my new function. This is the point -pi over 2, 2. This is the point 0, 1. This is the point pi over 2, 0. All right, that's how you do sketches of cotangent and tangent. All right, let's move on to our other functions, secant and cosecant. Okay, so the graphs of secant and cosecant are related to that of cosine and sine, respectively. Now, I intended to put the sine function on here, and I didn't. I put a transformed version of the sine function, so I'm going to go ahead and just sketch the sine I'm going to say that's pretty good. And so ignore the red graph for a moment. But cosecant is equal to 1 over the sine of x. All right, so anywhere that sine x equals 0, which would be at each of these locations at 0, pi, 2 pi, negative pi, and so on and so forth, 1 over 0 would be the cosecant of x. And 1 over 0, of course, is undefined. That's going to represent a vertical asymptote here. Again, ignore the red graph, just focus on the black graph here. All right, now what would I get if sine x equaled 1? Well, if sine x equaled 1, then cosecant of x would be 1 over 1. So it would also be 1. So anywhere that the sine is 1 or negative 1, so is the cosecant. Okay, so they're going to share that point. It's going to be the only point that they share. Okay, at each of those local maximums and minimums. Now, as the sine value decreases, right? So for example, sine of pi over 6 is 1/2. Right, so if I go to pi over 6, which is about right here, the sine is 1/2. If I took 1 over 1/2, I would get 2. So the cosecant value is actually 2. And symmetrically, at 5 pi over 6, the sine is 1/2, and the cosecant of 5 pi over 6 is also 2. So I'm going to sketch this portion of the cosecant graph, and then each of the subsequent portions, and this is not to scale or perfect by any means, but you can see that the graph shares that one max or min value from the sine function repeatedly over and over again. Okay, so the yellow graph is the graph of y equals cosecant of x. Now the period of cosecant is 2 pi. Okay, you can see from here all the way over to this asymptote, that is one cycle, provided there, I mean, obviously there is a discontinuity with those vertical asymptotes, but the period of cosecant and secant is still 2 pi. Okay, let's look at the secant function based on cosine. All right, the secant function based on cosine is going to be done very similarly. The asymptotes are just shifted pi over 2 units. So the secant function is going to look almost identical to the cosecant function, except there's just a shift involved. And really, that's all that the difference is between cosine and sine. Okay, that's the only difference between cosine and sine. Cosine function is just a shifted sine function. So that is the basics of cosecant and secant graphs. Let's go ahead and do a couple of examples. All right, so I'm going to apply the transformations that are given here, and I'm going to sketch just one period. So whenever I see a secant function, I think cosine. So I'm going to graph cosine, and I'm actually going to graph negative 1/2 cosine x. So I'm going to graph negative 1/2 cosine x. So in order to do that, I'm just going to graph cosine x. Okay, so I got cosine x from 0 to 2 pi, and pi over 2, and 3 pi over 2. Okay. I'm going to then graph cosine, and I know how that goes because we do it repeatedly. We do it over and over again. Get really good at sketching those out. Okay, I'm going to flip that. So this would be negative cosine x. Okay, y equals negative cosine x. And then a simple adjustment that I make in order to scale this is I'm going to then call this negative 1/2 and this positive 1/2. And that changes, just by labeling, changes that graph to negative 1/2 cosine x. Now I'm going to label a couple of points here. One of which, actually I'm going to label 3 points. All right, this is going to be, I don't know, let's go with, this is the point pi 1/2. All right, so pi 1/2. All right, now with regards to the cosine function, the secant function, wherever the cosine function is 0, the secant function has an asymptote. So I am going to graph one full period, however, it's going to be split into 3 chunks. So let's graph the secant function. And looky there. I got one period of the secant function there in yellow. This is the point, again, pi 1/2. This point right here will be the point 2 pi negative 1/2. And this point right here is the point 0 comma negative 1/2. And there's the graph of negative 1/2 secant x. Let's move over here. Secant pi x minus 3. Okay, so I'm going to think period first. Period will be 2 pi over pi. Oops, pi. So the period is 2. This is interesting. Okay, and then I got a vertical shift down 3 units. So I'm going to draw a cosine. And now instead of from 0 to 2 pi, I'm going to just draw it from 0 to 2. So this would be 1, 1/2, 3/2. Okay, this would be the point 1. This would be the point negative 1. And just business as usual here, just now not including pi. I've got the sketch right there of y equals cosine pi x. All right, now I'm going to shift it down 3 units. So this point right here will go from 1 down to negative 2. All right, I'll try to do this proportionally, make it look nice. So this is going to go from 0 down to negative 3. So our baseline went from 0 down to negative 3, which makes sense, right? Shift down 3 units, perfect. This point's going to go from negative 1 to negative 4. This point will go down to negative 3 from 0 and from 1 to negative 2. So this would be a graph. That right there is the graph of y equals cosine pi x minus 3. So how do I turn that into secant pi x minus 3? Okay, so wherever the zeros were, right, now the zeros will be, right? Even though it's not a 0, that is where the vertical asymptote will be located. Okay, so I'm just going to go ahead and do a number on that. Okay, and then I'm going to sketch my function. And I don't have enough space down here, but that's the general behavior that that graph would take on. This point would be the point 1 comma negative 4. This point would be 2 comma negative 2. And this point would be 0 comma negative 2. And there you have y equals secant pi x minus 3. A couple more left. Okay, cosecant. Really dumb joke, but my dad used to tell this. He's a former math teacher, but he used to tell this joke about how when he'd go to weddings, people would ask him, you know, do you like to dance? And he'd just look at my mom, his wife, and she'd say, do you know what his favorite trig function is? And she'd say, cosecant. And no one would understand the joke, so it's really not that funny, but he can't dance. Cosecant. Yeah, really dumb. Okay, so let's graph y equals 3 sine of x over 2. Okay, so period will equal 2 pi over a half. So the period will be 4 pi. So let me sketch out here to 4 pi. Halfway will be 2 pi, pi. Love working with 4s. And 3 pi. Okay. Sine, if its amplitude is 3, this would be a 3, -3. No vertical reflection, no vertical shift, no horizontal shift. This is going to be a nice one. Okay, so we're going to get something like this. Let's do our general sketch of sine. And now we go with cosecant. Okay, this is really nice. There's no shifts, nothing. So all we got to do then is find our asymptotes, which is wherever we would get a 0. And then we're connecting some points, my friends. So our function kisses the sine function right there at 3 pi -3 and at pi 3. And we got ourselves a cosecant graph. Of course, now the period is 4 pi, as you can see. From beginning to end of one cycle is 4 pi units. All right, let's do one more. Negative cosecant of x over 3. This will be nice too. Period will equal 2 pi over 1/3. Not as nice, but whatever. 6 pi. So I'll go out here to 6 pi. Half of that will be 3 pi. Half of that will be fraction. That's what I mean by not nice. So that'd be 3 pi, 6 pi. Excuse me, 3 pi over 2, 6 pi over 2. That'd have to be 9 pi over 2. And then this would be 12 pi over 2, which is 6 pi. Okay, so no change in amplitude. 1, -1. However, the graph of sine will be flipped. Right? Vertical reflection. Oops, that was my bad. 0, and then -1 instead of +1. I'm getting kind of tired, but that's okay. Drive on. Put a little Tabasco under the eyes. No big deal. All right, asymptotes. Let's sketch them. Here we go. And there you go. Now, again, a little kiss there at 3 pi over 2, -1, and another there at 9 pi over 2, 1. And with secant and cosecant, if you have a situation like this, I'm really okay with just those points that identify the local max and min. You don't have to find points, in this general area here. Of course, like a graph like this one, you'll have 3 points naturally because there's 3 local maximas or minimas. But you guys, that's how you graph those reciprocal functions: secant, cosecant, cotangent, and then of course that staple function of tangent. That is lesson, I believe, E is an echo. If you got any questions, let me know.